Okay, let's talk a little bit about organic chemistry. Organic chemistry is a study of carbon-containing compounds. If those organic compounds are used in biological systems, we call that biochemistry. Most of them consist of carbon and hydrogen and perhaps some other atoms, which we'll talk about a little later. So we'll review from first semester. We talked about molecular geometry, and that tends to come in a couple of different varieties, as many organic molecules obey the octet rule, which means they have 8 electrons in the finished structure, which makes it somewhat easy to draw basic organic molecules. Many carbons are tetrahedral, which is an sp3 hybrid. If you're unsure about some of this, go back and look at some of the first semester videos where this is talked about in detail. But the orbitals of 4 sp3 hybrids, you get 4 single bonds per carbon. For example, ethane has 2 carbons, 6 hydrogens, and what we can see is that each carbon has 4 bonds, where one of those is a carbon-carbon bond and the other 3 are carbon-hydrogen bonds. What we find is that carbon forms chains and sometimes even branches, but it's got 4 single bonds around it in a tetrahedral geometry. Carbons are never the outer atom, at least in these basic molecules, and so you should be thinking of these carbons connecting to each other and then to perhaps other atoms like hydrogen or oxygen, for example, but never an outer atom. They're always a central atom. So don't draw them as an outer atom. As such, if you just got carbon and hydrogen, you string the carbons together in the appropriate structure, add the hydrogens to complete the 4 bonds that are required. Now, trigonal planar is an sp2 hybrid, so it has 3 sp2 hybrids and 1 p orbital kind of hanging out. That means you're going to form 3 sigma bonds and 1 pi bond. Now, sigma bonds are head-to-head overlap of the orbitals, and a pi bond is side-to-side or top and bottom overlap of the orbitals. Again, you can refer back to the first semester material for some more detail on that. Ethylene is 2 carbon atoms bonded together, but with a double bond, and the remaining going around for hydrogen. Now, if I don't have enough hydrogens to complete that structure, that implies I'm going to need a double bond to complete my octet. And you can draw these out with the rules we used in the first semester course, or you can actually infer it somewhat in simple molecules. sp molecules are linear, has 2 sp hybrids and 2 p orbitals that weren't hybridized. So it's got 2 sigma bonds and 2 pi bonds. A triple bond represents a sigma and 2 different pi bonds. You get a linear molecule like acetylene. So now I don't have enough hydrogens even for that double bond situation, so I'm going to need a triple bond to satisfy the octet rule. And you have to practice being able to draw these, and we'll work through some of that. So here's some examples. Here's our friend methane to the far left. It's an sp3 hybrid, therefore it's tetrahedral. And you see that tetrahedral geometry with a 109-degree bond angle is really 109.5 degrees. But it's an sp3 hybrid. Something like formaldehyde there in the center is an sp2 hybrid. It's trigonal planar and has 120-degree bond angles. Because you see there's 3 total bonds. Yes, you have a double bond, but it's 1 double bond, not 2 different bonds. And so that gives us a trigonal planar geometry. Remember, multiple bonds only count once for the geometry. And then we got that acetonitrile, where you've got that carbon-nitrogen triple bond, but that gives us only 2 total bonds on that particular carbon. And that carbon attached to the nitrogen is an sp hybrid. The other one is tetrahedral, but we're going to focus on the sp hybrid 180-degree bond angles. So hydrocarbons or organic groups contain only carbon and hydrogen, and that's be the primary focus of our organic in this particular section. You got alkanes, where you have all carbon-carbon single bonds. Alkenes, you have at least one carbon-carbon double bond. You could potentially have more than one, but at least one. Alkynes, YNE, at least one carbon-carbon triple bond. Aromatics have a planar ring structure with alternating single and double bonds like benzene, which we talked about first semester. So if we just look at this flow chart, we've got all hydrocarbons, then we got what we call aliphatic versus aromatic. So anything that's not aromatic, like say our friend benzene, is going to be aliphatic. And so we can have hydrocarbons that are saturated, meaning they don't have any double or triple bonds in them, like alkanes and cyclic alkanes, which we'll talk about both. Or they can be unsaturated, like alkenes and alkynes, and even our aromatics are unsaturated, meaning they have at least one double or triple bond in them. So as we were saying, saturated have only sigma bonds or single bonds, no double or triple bonds. So unsaturated compounds have a mixture of sigma and pi bonds, meaning they have single bonds in them, but also double and triple bonds in all likelihood. So here are some pictures of some of these structures. So an alkane like ethane, you can see it as a space filling model, and you can see it as a structure to the far right that illustrates its geometry, where you got one coming towards you, one going away, and one in the plane of the screen. Then you got ethylene or ethene, carbon-carbon double bond. And so now this molecule lays a little bit more flat depending on how it's oriented. Acetylene is definitely a flat molecule, 180-degree bond angles. The aromatic has alternating single and double bonds in this ring, 120-degree bond angles. Now, since the bonds are alternating single and double bonds throughout the ring, sometimes they'll just draw a circle in the middle of the ring to illustrate that, and we'll come back to talk about that. But benzene has a formula C6H6 and exhibits resonance, which we talked about in the first course. Next time we'll pick up with a discussion of alkanes.